Okay, now that we know something about acceleration, I'd like to take a look at a specific example of accelerated motion, and that's something called freefall. And freefall is a special case where you imagine an object falling where the only force acting on the object is gravity. So, and this is the case of an object falling acted upon only by gravity. So what does that mean? What are we ignoring? Well, principally what it means is that we're ignoring is air resistance, which is a sort of an upward force. So you have an object falling, the air kind of pushes up on the object as it falls, and we're going to ignore that force. So ignore air resistance. And it turns out, under certain circumstances, you have to make a few caveats, but on Earth, if we assume certain things to be true, such as an object is falling from a reasonable height. In other words, we're imagining an object that's falling from maybe several hundred feet falling to the ground, as opposed to 50 miles up and falling to the ground. So if you go way, 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 way high up, and you fall from a tremendous height down to Earth, then this wouldn't be true. But under most ordinary falling circumstances of an object falling, the free fall, the acceleration that the object experiences due to gravity is going to be a constant. It's a constant acceleration. So this is an example of a uniform free fall acceleration. And it's a very important value, so much so it gets its own letter. We call this little g. So little g is the what we call gravitational acceleration, or the acceleration due to gravity. If I drop an object on Earth, it will fall, and as it falls faster and faster and faster. It accelerates, and that acceleration is the acceleration due to gravity. Do not, I'm telling you right now, do not refer to little g. This is not gravity. When you use the word gravity in physics is a force. Little g is an acceleration that is produced by that force. So little g is the acceleration due to gravity. If you ever refer to little g as gravity, I will likely be angry and throw things at you. So this is little g, the acceleration due to gravity. Now, little g, we'll find out later in the year, it's a result of how big the Earth is, how much mass there is. Suffice to say, on Earth, the acceleration due to gravity on Earth is very close to 10 meters per second squared. It's 9.8 meters per second squared. Very, very close to 10. It's nice that it's very close to 10 because you can frequently ballpark answers to problems without doing any, or without needing to resort to a calculator. So this is the acceleration due to gravity on Earth, which means that an object is always going to accelerate at 9.8 meters per second squared. Now, one thing I'm going to throw in here, usually, we make this negative. Why do we make it negative? We make it negative because we almost always think of down as the negative direction. So it's down, and we like to generally think of down as the negative direction. So the acceleration due to gravity is always down. Gravity pulls objects down to the Earth, and so we think of it as being a negative value. Let's, in order to maybe try to understand the acceleration due to gravity a little bit, it might be nice to think about a pretty straightforward situation, and maybe draw a velocity time graph might be helpful. So here we have the ground, and here's our person standing on the ground. And this person is holding a ball, which they're going to throw up in the air. So they throw this ball up, and up it goes. And as it goes up, it's going to experience a negative acceleration, so it's going to decelerate. It's going to slow down to a stop. And then after it slows, after it comes to a stop, it's now going to experience a negative acceleration downward. Well, if it's going down with a negative acceleration, what's going to happen? It's going to speed up. So it goes up and then down. Bear in mind, this is kind of tricky, right? Think about this. This is a negative acceleration, and the object is slowing, right? It's going up, but it's accelerating down, so it's slowing down. Here, on the way down on this side, it still has a negative acceleration. It's still negative 9.8, right? Where the acceleration due to gravity. Gravity is the only thing working here. We're imagining no air resistance, so the acceleration must be the acceleration due to gravity. But now it's going downwards. It's going in the negative direction, and it's got a negative acceleration. So what's happening? It is speeding up. If you haven't yet really kind of wrapped your mind around the relationship between acceleration, velocity, and speed, that might surprise you. By the way, before we move on, we're gonna make a graph of this in a minute. I could ask you, what's the acceleration at the very, very top? What is that acceleration? And some of you might be very tempted to say the acceleration must be zero because it's not moving. That would be an incorrect and naive answer. At the very, very top, there's still a force of gravity. The object is still accelerating. The acceleration up here is still negative 9.8. It's negative 9.8 on the way up. It's negative 9.8 on the way down. And it's negative 9.8 at the top. And you might be baffled by that. How, if it's not moving, is it accelerating? Well, remember, what acceleration means is that the object's velocity is changing. And even though the velocity at this instant of time is zero, an instant before it was moving, and an instant later it'll be moving down. And so even though the velocity is zero, the velocity is still changing. It is in a state of flux, and that's what acceleration is, a changing velocity value. If you still don't believe me, I would ask you to consider to yourself, what would happen if the velocity were zero and the acceleration were zero? What would that ball do at the very, very top? And it should be clear with a little bit of thought that if both the velocity and the acceleration were zero, the ball would reach the top, it would stop, and it would stay there. Because if it's not accelerating, that means the velocity isn't changing. It would remain zero, which clearly doesn't happen. So the acceleration the entire time is negative 9.8. From the moment it leaves my hand to the moment it returns to my hand. So let's make a graph of this. In fact, if you haven't done this exercise already, I would ask you right now, so this is a velocity time graph that I'm making here. I would ask you to pause the video even and see if you could, on your own, construct a velocity time graph for this scenario. What would it look like? So if you want to do that, you can. I'm going to go ahead and do it for you now. So maybe to make things easier, I'm gonna think of the trip up as segment A. A is the way up, and I'm going to think of the trip down as segment B. B is the way down. So let's see. The ball leaves my hand. What velocity does it have when it leaves my hand? Well, it's got a positive velocity. Mind you, this is an important point. I'm saying when the ball leaves my hand. So it doesn't leave my hand with zero velocity, right? The moment it leaves my hand, it's moving, and it's moving up. So it starts with a large positive value. So that's where we begin. And then the velocity diminishes, goes from some positive value down to zero. It's got a negative acceleration. So at the very top, the velocity is zero. So what's it going to have? It's got to have a negative slope, which shouldn't surprise anybody because we already said that the acceleration is negative. And if the acceleration is negative, then the slope of our line needs to be negative. So this is A. That's the part where it's going up. How about the part where it comes back down? You might be tempted to say, oh, well, it's speeding up, so I'm going to make my line go up. That would be wrong. Think about it. The acceleration is still negative. So the slope of my line needs to be negative. Why does that make sense? Because look, these velocities are negative velocities. The object is going downward, meaning the velocity must be negative. Down is the negative direction, up is the positive direction. So if it's going down, the velocity must be negative, and so I'm going to continue this line. So this is B. Okay? A and B. And this doesn't really look like it, but this should be a straight line. In fact, you may have already put this together. Hopefully you did. This has to be a straight line, and the slope of this line, the slope has to be exactly negative 9.8 because the acceleration is the slope, and the entire time the acceleration is negative 9.8. Even here, right, this point right here, this is that point right there corresponds to the top. This is when it leaves my hand, and this is when it returns to my hand. So it leaves my hand with a certain velocity. Let's say it's positive 10. It's going to return to my hand, and if it's free fall, it's going to return to my hand with exactly the same velocity, or exactly the same speed, but opposite sign. So in this case, it would be negative 10. If it left my hand positive 20, it would return to my hand with positive 20. So I think we'll leave it there for free fall. It's a brief introduction. Again, more practice in class.